Alrighty, welcome back, honors chemistry students. I am filming this video in my bedroom downstairs, so just be patient with me. I'm gonna try to make the best of it using like this little makeshift whiteboard and everything. So hopefully you'll be able to see everything, and just let me know if you have any questions. So today we're gonna start talking about half-life. So what is a half-life? You've probably heard of a half-life. I've given you like a little inkling about half-life because we've already talked about beta decay and alpha decay and gamma radiation, so that connects to all of this as well. So, so half-life is the time for radiation level to fall or decay to 1/2 of its initial level. Okay, so if we start with 8 milligrams, if we get to 4, it's 1 half-life. If we get to 2, it's a second half-life. If we get to 1, it's a third half-life. Okay, so the time for the radiation level to fall to 1/2 its initial value. So half-life is basically just how long it takes something to decay. If you need more time to write down notes, just go ahead and pause the video. Our formula you're going to be using to solve half-life is A equals A naught times 1/2 T over H, where A is our final amount, A naught is our initial amount, A0, that's what that little thing means, it's our initial amount. 1/2, it's a split factor. T is time as usual, and H is going to be our half-life. And I'm going to show you how we can rearrange this formula as well. It does get a little bit confusing when we're solving for this formula because we're going to be using log and ln. So it does get pretty heavy in the algebra and math side of the stuff. Sorry, I just realized I have chocolate cake batter on my chin, so that's embarrassing. It was delicious, though. All right, let's do a practice problem together. So the half-life of I-123 is 13 hours. How much of a 64 milligram sample of I-123 is left after 26 hours? I'm going to pause for a moment and write this down on our whiteboard, and then I will go over this with you. Alrighty, sorry, my lamp is right on in the middle of everything. So our first step, like we do with all math problems, is we are going to identify what our different variables are. So I told you that I-123 has a half-life of 13 hours. It's a 64 milligram sample, and we're going to see how much time elapses after 26 hours. So when we are locating this, our initial amount, our A naught, is always going to be an amount in grams or milligrams. It's going to be how much we're starting with. And it tells us we have a 64 milligram sample. Okay, so our A naught, our initial value, is 64 milligrams. Our next little thing we're looking at, we're always going to have half time. Our time is how much time has gone past. Okay, and it tells us that our T is, we're looking at 26 hours. And then we also have our H here, our half-life. Our half-life, our half-life is 13 hours. I don't know what I'm doing right now. And we're looking for this A. We're looking for our final amount. Okay, so what we're going to do is just plug those in. So we have A equals 64 times 1/2, 26 over 13. And then you can just go ahead and solve this. 26 over 13 we know is 2, so it's 1/2 to the second times 64, which gives us an answer of 16 milligrams. That is how much is left after 26 hours has elapsed if our half-life is 13 hours. I know you guys can generally solve these using just like quick what's the word I'm looking for? Just like a process of like, oh, what's half and half and half and half and half. But I would recommend you use this formula so that it makes more sense to you, and it's a lot easier to do, and it guarantees you get the right answer. So that's the formula you're going to use when solving, when solving a problem for A. You can also sometimes search for H. You can also sometimes search for T. So I am going to give you the formula when we look for H, for our half-life. So when we're trying to find the half-life, our equation is going to be H equals T times log of 1/2 divided by log of A over A naught. So, like I said, this gets a lot more into the algebra side of things. Let me know if you have questions on this. If you know these two formulas, you will be okay though, okay? So just remember these two formulas, and as long as you know where the log function is on your calculator, you will be okay. Let's head on back to the PowerPoint then. So that's the problem we just went over. We're going to go over a little bit of fission and fusion. I know we started this at the very beginning of the year when talking about the different types of chemistry. So now we're just going to get some notes on the difference between the two things. So, nuclear fission. Fission is when large nuclei break up, so things separate. Okay, as you can see here, you just learned how to do this. So we have utopium, and a bombardment of a nitrogen particle gives us, I believe this is barium, krypton, and 3 more neutron particles, and energy. Okay, so nuclear fission is when things are breaking up. So we start with 1 and we end with 2. Whereas nuclear fusion is when small nuclei are combining. Fusion, it happens in the sun and other stars. Okay, again, things are combining to make something bigger. So you can see we have 2 different isotopes of hydrogen combining to make helium. Alrighty, just a little learning check for us. I want you to pause the video really quick and identify in which one does the nucleus split, fission or fusion. And large amounts of energy are released, is that fission or fusion? Small nuclei form larger nuclei and hydrogen nuclei react. Classify each of the following as this. Some of them might be more than one. So the nucleus splits. We know that fission is when things separate. In both fission and fusion, energy is released, and it's a lot of energy being released, okay? Fission and fusion, as you know, fission and fusion have to do with bombs. They're not something that happens regularly. Scientists took a long time to figure out how to do this. I don't remember which one it is, but we're just starting to figure out how to fuse 2 things together, and it creates a large amount of energy, but it also takes a lot of energy. In fusion, small nuclei form larger nuclei, and also in fusion, hydrogen nuclei are reacting. Alrighty, those are all the notes we're going to go over for half-life. I do have a separate little video that goes over another example problem with half-life. As long as you know those 2 equations, so you should be okay on your practice problems, but let me know if you have any other questions. I haven't decided if I'm going to give you those formulas yet on your test. If you've watched this whole video, email me your claim on whether or not you should get them, and I'll see how nice I'm feeling. Alrighty, have a great day.